Welcome to the Walton Pie. Today I'm going to do a math meme review where I'm going to just explain the memes until they're probably no longer funny. But because it's April Fool's Day today and I wanted to have some sort of pranky video, but I didn't want to do something that was actually wrong like I did last year, so if you want to see that, go ahead and check that out. But I'm going to go through a bunch of memes that my roommates were willing to make for me, and so I'm going to go through and basically explain the math behind these, probably to the point that it's no longer funny. So I hope you're ready for a fun time, because here we go. Let's see. Okay, Epsilon is expected to... Okay, so this one's really funny, mainly because in math we use epsilon to represent something very small, and then we usually have epsilon be heading towards 0, so epsilon is normally, if you see epsilon in a proof, it's representing a really small thing. So this is from back in 2020 when there was the tropical storm Epsilon and it was getting really, really big. And that is entertaining because Epsilon normally gets really small. So there you go. There's your first math meme explained, so it's probably not funny for any of you anymore. Okay. 77 plus 33 is 100. Okay. Oh, that's clever. Okay. So for this one, if you write numbers in base 9, that means so our normal system is base 10, so we count up through 10, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10, we have to include a new digit. So everything in the tens place, so that would be right here, all of those things are going to be worth 10 things, whereas here, because we're in base 9, these are worth 9s. So 33 in base 9 is 3 9s, and 3, so that's a total of 30 in base 10. So this is 70 plus 30 is 100. So that's how this one is playing out. Let's see. Useful geometry formulas. Pi r squared. See, that's a circle. That's not a sphere. And okay. Oh. Oh, that is... Oh, no, that is... Okay. So this is not finding the volumes of anything, but finding the areas if we just ignored all the other lines signifying this. So this first one, this is a circle with extra stuff that is not needed. So we don't need this line or this dotted line. And we just have a circle of radius r. So its area is pi r squared. Then this one, what we have is the area of an ellipse is pi times a times b, and so we're only taking half of the ellipse, so the bottom half, and then we're taking this top triangle which has area base times height, because the base is 2 times b and then the height is h, and then they're doing the same thing here. So we have a pi r over 2 plus h times d. That's again just, oh, okay, this is, do not use this when you're trying to do your formula things, because yes, that's right for the areas of the shapes if you ignore the fact that we are trying to represent 3 dimensions here. Let's see, if the limit as n goes to infinity of a sub n is 0, then the sum from k equals 1 to infinity of a sub k converges. Oh, okay. So this one's actually a really good example of a common mistake that a lot of people make when they are doing stuff with sequences and series, is the theorem says what Batman is saying. So if the limit as n goes to infinity of a sub n is not 0, then the sum of the a sub k's will diverge. That does not mean that if the limit of the a sub n's is 0, then the sum is going to converge. That's not what this is saying, because that is actually a very common mistake. We can't just negate the implication and negate the conclusion. That's not going to be true. And so that is a very, very common mistake that a lot of people do actually make. And so I guess having it in a meme is going to help it so that a lot of you will remember that better. So there we go. Let's hope that this helps understand mathematics a little bit better. Okay, so x plus y all squared is equal to, and then everyone in the group is just saying x squared plus y squared. That is a very, very common mistake that a lot of students make. I think the last test that I was grading had at least 20 students make this mistake on it. So this is a common mistake that just a lot of people make, this is not always true. So if you're trying to figure out why this isn't true, let x be 1 and y be 2. Then x plus y all squared, that's 1 plus 2, that's 3 squared, so that should be a 9. But then 1 squared plus 2 squared, that's 1 plus 4, which is 5. So that's why those aren't always going to be the same. Let's see. Okay, Corbett needs you to find the differences between this picture and this picture. Oh, okay. So these are both just different ways of writing an ellipse. The x squared over 4 squared plus y squared over 3 squared equals 1. That's a common way that we see it in like calculus classes. But then the xy vector form, so that's what the other one is, that's often when we start to talk about parametric equations. So these are both equations of an ellipse. The first one is just giving us all the points that go through it, whereas the second one is giving us a path that will cover the entire the entire boundary of the ellipse. So that's why these are the same picture. They're both representing the same collection of points. Okay, I don't know what that equation's representing. T is net rate, M is unit mass. We have flow balance and decorative. Okay. Okay, so this time XKCD, what he's doing is he's just saying, well, if it doesn't look complicated enough, just add extra constants to make it look more complicated, which I honestly think is what some people do in their papers and stuff, because a lot of those things are way more complicated, way more complicated than I think they need to be. I personally like things when they're very simple looking. I find that really beautiful, but a lot of things aren't always that way. And sometimes the constants are just absolutely out of whack and just covering everything, and there's just way too many of them. So that's also a very real possibility. Let's see, if x squared equals 9, then x is 3. My math teacher. There is another. Yeah, this is another one. So a lot of times students will forget that both the positive and negative of a number, when you square it, will become the positive thing. But an important thing to remember is the square root function only ever gives the positive thing. So the square root of 9 is 3. But there are two solutions to x squared equals 9. So that's why if you solve for x, the square root of x squared equaling the square root of 9, that's where you get x equals plus or minus the square root of 9. That's where that plus or minus is coming from, because the square root only ever gives us the positive answer. Let's see, I fear no man, but that thing, lemma 36.2, it scares me. Yeah, so a lot of times lemmas are not as easy as we would think they should be. So a lemma is just a theorem that we use to be able to get at a bigger result that is our goal. So lemmas oftentimes are these nice, short, little, small little results that we're able to prove that then we're going to be using frequently in the proof, and so we just want to prove it beforehand. But other times, those lemmas are terrifying because they are incredibly technical. They have a lot of very specific terms that you have to do. Sometimes they're really hard to be able to prove, but the reason they're a lemma instead of the main theorem is their use is pretty much just to prove that big theorem, because the big idea is we have lemmas, theorems, and corollaries, or corollaries, depending on how you pronounce things, where a lemma is a result used to prove a theorem, which is our end goal, and then a corollary, that is going to be a quick result that we can get once we've finished our theorem. So you can think of the theorems as a lemma to a corollary. If that didn't make much sense, don't worry, it's not too terrible. It's just lemma, corollary, and theorem. Those are all different things to say this is a result that we proved. Let's see, physicists and a pure mathematician, applied mathematicians, prove the Navier-Stokes equation, existence, and smoothness. Yeah, so there's a lot of problems from physics that are very math heavy, and the Navier-Stokes equation, those are some equations that are very, very useful for physicists, but they have not been proven mathematically rigorously because they are very hard problems, and if you solved them, you would probably get a Nobel Prize. They are very, very hard equations to be able to actually solve, and we actually don't know if they are even able to be solved. So if you want a fun project, jump on in that and you can win yourself a Nobel Prize. Let's see, you have to respect other people's opinions. Their opinion. Inverse tangent of x is 1 over tangent of x. Okay, so this is also another really common mistake that a lot of people make, is that the inverse, the -1 symbol, that just means, oh, it's just 1 over that, which is a very common mistake, because if you have a variable to the -1, that's 1 over that variable. But if you have a function to the -1, it's not 1 over the function. That's often representing the inverse, which is very confusing because we have the same notation for both of them. I totally understand why this mistake happens a lot, but that's the main reason that we have the functions cotangent, cosecant, and secant, is to have a function that represents 1 over tangent and 1 over sine and 1 over cosine, so that we don't have to figure out, oh, do they mean tangent to the -1 or do they mean inverse tangent? Because that gets confusing. And so if you see tangent to the -1 or cosine to the -1 or sine to the -1, that means the inverse function, not 1 over that function. But yeah, that is a very understandable one and a very common mistake that a lot of students make as well. Let's see, when the theory of computation professor says the proof is trivial. Oh, okay. Yeah, a lot of people like to say that the proof is trivial. One of my favorite quotes, I don't remember who said this, but there are only 2 classifications of proofs, trivial and impossible, and there is a fine line that manages to intersect both of them. So a lot of things, if you've seen it a lot, feel trivial, but oh my goodness, are they not trivial when you are trying to figure them out? I really, really hate it when my textbooks are saying, and the following proof is left as an exercise to the reader. Like, no, please, I'm reading this because I don't understand what's going on. Please just tell me. And yeah, it's tricky. Like, most things are not easy to prove, especially when it's your first time seeing it. So yeah, if it's a math major, you've probably seen these type of proofs before, so yeah, you're going to be like, oh yeah, De Morgan's laws, I know what those are. But everyone else, including you when you saw it the first time, were like, I have no idea what's going on. So I feel the pain of the CS majors in this one, so trying to understand the proofs are not easy at all the first time you see them, or the second time, or the third, or usually the 4th, 5th, 6th, or 7th. It takes a lot of practice to start to understand proofs. Okay, given these prevalences, is it likely that the test result is a false positive? Well, this chapter is on Bayes' theorem, so yes. Okay, so Bayes' theorem is a way of, in statistics and probability theory, of trying to figure out what's the actual probability of something if I know something about the starting conditions. And so Bayes' theorem is a little bit complicated, so I'd recommend looking it up, but it basically says if you know the probability of something happening, you know the probability of some certain preconditions happening, and then you know the probability of those preconditions leading to a certain conclusion, you can use Bayes' theorem to figure out what's the actual probability that I am making the correct conclusion, which is very, very important and gets misused a lot or is forgotten a lot because it's not usually intuitive. So a lot of common sense things where, like for example with COVID, they are 95% accurate, but then let's say that 90% of people you test don't have it. That means that most positive results are actually false positives versus like actually being sick with COVID. But like with COVID, it would be much preferable to think that you have it but you don't actually, because then you're not out and about spreading the disease like a false negative would. So those are the sorts of things that Bayes' theorem is important to understand in those sorts of things. And not everything's going to be as severe as that, but a lot of those sorts of things are things that you would need to understand. So Bayes' theorem is a useful theorem because of that. Let's see, Calculus 2 teachers inventing the most unpleasant integral possible. Yeah, Calculus 2 is just rough. A lot of the integrals are tricky and not exactly the easiest things to do. And like even me, who's been doing integrals for 10 years now, I see some of those and I'm like, I don't know which method I should use because there's like 1,000 of them. And the trick is just trying them until you find one that works. And sometimes you don't know if it's going to work until you actually just do it. So, yeah, if you're in Calculus 2 right now, I feel you. It's doable, but yeah, some of those integrals are just rough. They're just rough. I wish a set of all sets. Yeah, so this one is really closely related to the idea of the power set. So if you imagine you have a set of all sets, then that means that every set is inside it, including itself. But then if you're trying to think about, then what's the size of that set? That is actually an impossible question to answer, which is a really cool thing to think about, to think what's the problem of having a set of every set, and then trying to figure out what the size of it is. It connects up with the barber paradox, where you have, like, in a town, a barber who shaves everyone in the town's hair, no one shaves their own head, and then the question becomes, who shaves the barber? Because the barber has to shave everyone in town, but then no one in town shaves themselves, so that means the barber can't shave himself, but he's in the town, so that means he must be shaven. And so it becomes this sort of paradox. A similar thing happens when you're trying to think about how big is the set of all sets. Because it has to be bigger than every set inside it, but then it can't be, so it leads to a lot of interesting things. So if you're really interested in that, I'd look up some set theory and try and think about, why can't I have a set of all sets? So that's the joke here. The wishing star is going to turn around before it has to grant that wish of having a set of all sets. Alright, sigma algebra or something. I never took probability. I don't get it. What Greek letters mean in equations? This math... Okay, so yeah, there's a lot of symbols in math, so let's actually go through and explain what a lot of these are. So this first one is the pi symbol, which either means pi, which is just the 3.14 that we all love, or pi comes up in other things, and sometimes pi is a function, and as soon as pi is a function, it's going to be a little bit tricky. So yeah, that's true. It's either simple or really hard. There's no in between with pi. Alright, let's see. So then this next one, this triangle, that's representing a delta, which means that something's changing. So that one's very accurate. The next one is a different delta, which is saying that something has changed and it's a mathematician's fault, which is definitely true, because we like to mess with things, and often we say, let delta be something small, we're going to have that be the change around a certain point. So yeah, that one's definitely true. Alright, theta. Yes, theta definitely represents angles almost all the time, unless you're dealing with like modular forms or other things, but that's a completely different topic. So yeah, theta's representing circles. Then this one, that's going to be our phi, so that's representing like your angle down when you're doing stuff with spheres. So you'll probably see that a lot if you're doing stuff with spheres. Okay. This one, that's our there exists symbol, or is an element of, sorry, not there exists, is an element of. So, yeah, if you either know what it means or you don't. Oh, I hate these letters. So, these letters are not V's or U's, but they are just mean. They look like U's and V's, but they're not, and when your teacher has not great handwriting and they have these equations on the board, they also probably have U's and V's on the board, and it's a nightmare to try and figure out what's going on. So yes, I hate those and I avoid them whenever I can. Okay, this next one's mu, and yeah, it's cool when those are the common variables, but yeah, it's not something that most of you will see, but you can use it as a variable whenever you want. It's great. Okay, and then for the sigma, it's saying, thank you for purchasing Addition Pro, because, yeah, that's just addition on steroids. You add a lot of stuff together, and you can add up infinitely many things with those. And then the big capital pi, that's the same thing but with multiplication. So you can have infinite products, which are super cool, but also a little bit confusing. Oh, there's more of them. Okay, so the first one's zeta, which, yes, it gets used a lot in number theory. So if you want a really cool function to look at the Riemann zeta function, and that's where the Riemann hypothesis has to do. So there's a really big $1 million unanswered question involving zeta. So go ahead and try and figure that out. It's a tricky one. Okay, yep, beta gets used when you run out of coefficients. Let's see, alpha. Okay, my guess is this is now some sort of like engineering stuff, because I use alpha and beta a lot together, but yeah, okay. And yeah, this is where he's starting to make fun of mathematicians. If you're using capital omega, then yeah, either you're talking about a set or you think it's a cool or something. Yeah, let's see. Little omega. Yeah, that's fair. Going to die among the equations, that's fair. If you have a lot of variables, it's going to take you a good half hour to get through a few lines of that to try and figure out what's going on. And yeah, some poor soul trying to apply math to real life and it's not working. Yeah, the real world is tricky and math does not work perfectly. It's the best thing we got, but some of those things are not exactly easy to do. Oh, yeah, Xi. This one is Xi. And yeah, I'm trying to write it, and then also anytime it shows up, I just want to die, because it is absolutely terrifying whenever it does come up. Okay, and then this last one's gamma, and yeah, it's fun to write. I like doing it. Okay, rho, the test vehicle suffered an unexpected wing separation event. I don't understand what that's referencing, but it's funny. And yeah, these ones, if you're coming across these, you're in for a wild ride. Alright, let's see. 0 to 0 is undefined. Yeah, that's the accurate thing. 0 to the okay, no. 0 to the 0 is not 1. 0 to the 0 is undefined. We don't know what it is, depending on the circumstances, and so you're going to have to take a limit of whatever's going towards the zeros to figure out what's going on. It is not 1. So, sorry if this one's, like, a little triggering for me. Like, no. Like, 0 to the 0 is undefined. It is not 1. Alright, yeah. Pi Day, just a fake holiday created by math companies to sell more math. Well, here's the thing. We don't need to sell more math. You are all going to do math frequently in your life, even without recognizing it. If you go out and play catch, you're tracking parabolas with your eyes, and you're going to predict exactly where the ball is going to land so you can catch it. Like, you do a lot of math, like, unconsciously or subconsciously without recognizing it. So math gets used a lot. But yeah, Pi Day, a little bit arbitrary that we say, okay, everyone celebrate on March 14th. But that's only because in America we do month and then day. Imagine if you do day then month. How are you supposed to have 314? There's not 31 days in April. So if you're doing it there, then we actually celebrate it on July 22nd, because that's 22/7, because 22/7 is actually a really good approximation for pi. It's not exactly pi, but it's pretty close. Alright, let's see. To solve this equation, we invoke Gauss's operator to transform it into a dragon. Then we slay the dragon with Hilbert's arrow and transform its corpse back into the solution. Just to be clear, this is a metaphor, right? Does this look like an English class? Yeah, this is definitely what higher level math comes across as, and feels like sometimes. You're like, I'm not sure where these are coming from. I don't know why you decided to name them these things, but yeah, this is definitely what some of my math classes have felt like. And yeah, this is a great XKCD comic. Alright, let's see. Yeah, this is what I was talking about. The idea of the existence of such and such is left as an exercise to the reader. Like, no, you do not want to ever come across that, because those are not fun to try and figure out. But the first one, that's pretty nice. It's saying, hey, look, here we go. We have all of these things. It's telling us exactly what it is going to be. But trying to find it, yeah. It's not fun when you're like, the following is left as an exercise to the reader. So one time, on one of my assignments, I just ran out of time to finish it, so I wasn't able to finish everything. So on the last problem, I just said, the existence of a proof is left as an exercise to the grader. And when I got it back, I got completion points on that problem, which was so funny. And I hope the grader got a laugh out of it as much as I did. So I hope she enjoyed it. Okay. Limit as x goes to infinity of 8x squared over x is infinity. So then the limit as x goes to infinity of 5x squared over x is a sideways 5. Yeah, so it's just a coincidence that 8 and infinity look like each other rotated 90 degrees, or pi half radians. But yeah, it's just a coincidence about that, so yeah, I enjoy that one. That one's funny. What does this look like to you? Looks like a hat, then you're an adult. If it looks like an elephant being eaten by a boa constrictor, you're still a child at heart. If it looks like a bimodal Gaussian distribution, you're in a statistics and your life is over. That is so true. I have a hard time with statistics. I like to call it sadistics just because it's not easy for me to do, but very, very important. But it is not easy. It is not easy at all. Alright, the simplest explanation is that Occam shaves the barber. Okay, so this is actually going back to that barber paradox I was talking about. So you're in the town, there's a barber, he shaves everyone's head in the town, and no one in the town shaves themselves. The question is, who shaves the barber's head? Well, that's being mixed with Occam's Razor, which is not an actual razor that you would use to shave with. It's the idea that if you have two or more possible scenarios of how something happens, Occam's Razor says, take the one that takes the fewest assumptions. So, for example, the fact that we have dinosaur bones that we find. We have option 1, dinosaurs existed and we're finding their bones. Or option B, all of this was put there as a government conspiracy to convince us that evolution's a thing. Which one of those takes fewer assumptions? Assumption 1 for dinosaurs existing is there were dinosaurs before us and then they died. For the other one, it's saying the government wants us to think that there were dinosaurs before, and they have a group of people hiding dinosaur bones, and we haven't heard anything from them because we are assuming that this somehow government conspiracy keeps putting bones in rocks and that they are not having anyone accidentally let slip about that. One of those has a lot fewer assumptions. Occam's Razor says, drop the one that has more assumptions and keep the one that makes more logical sense. In this case, dinosaurs existing. Alright, flag of Nepal. Okay. So, yeah, Nepal's flag is weird. It's not a rectangle. But apparently it also has a ratio of side to width of an irrational number. So, that's cool. I didn't know that. When the ratio test and the root test fail. Yeah. So both of those are used to be able to figure out if a power series or, in other times, a improper integral are going to converge. And sometimes those tests don't work, and they are the nicest of the tests, so yeah, it's not great when that's the case. Every single thing that exists in this infinite universe is either a duck or not a duck. That is true. That is very, very true. You can definitely break things into the things that I can see right now and the things that I can't, or the things that are made up of a single atom and the things that are not. All of those are very valid, categorizations. Let's see. Sketchy proofs based on infinitesimals. Do you trust me? Physics undergrad with every cell of my body. Yeah, in the physics classes I took, they definitely were very skimpy on the details and the rigor. But if you're in physics and you want the more rigorous thing, take a math class. They're fun. Alright. Says here you should be in hell, but since you studied statistics, we'll count it as time served. Told you statistics is really sadistics. It's not easy. At least for me it's not. If it's easy for you, congratulations. It's very, very useful and very important, but oh my goodness, is that hard for me to focus on and understand. Yeah, these are the good books. A mathematical analysis book where the proofs are not left as exercises for the reader. So there's a project that a group of mathematicians did where they tried to rigorously prove everything and have a very structural, rigorous basis for things. And I think it took them 300 pages using set theory to prove that 1 + 1 is 2, which is impressive that you can prove it. Because think about what minimum assumptions you would have to make to then be able to have a conclusion that 1 + 1 is 2. Most of the time we just assume that's the case. But that project, very impressive. But at the same time, that book is so hard to read. It is so notation heavy. Yeah, that one's a hard one. Oh yeah, this is a cool function. I think this is the function that is nowhere differentiable, which is super cool to think about. How can you have a function where the derivative doesn't exist anywhere? And it turns out it's mainly because this is fractally, which is super cool. I like that function. Alright, e to the x, exp of x, and arcln of x. So all of these are different ways of just saying e to the x. So exp parenthesis stuff, that's how you write e to the power of stuff when there's a lot of that stuff and you don't want it to all be really small in the text. So exp of stuff, that's just saying e to the power of everything that's in the parentheses. But then the last one, arcln, I've never seen that one. And that's just because arc in front of a trig function, like the one that we were talking about earlier with the inverse tangent, which was there, that one, you can write tangent to the -1 as arctangent, and that's another one that's a little bit easier of one to be able to understand. But here they're just sticking it in front of ln for no reason, because e to the x is the inverse function of natural log, but oh, I've never seen that before. Thank you so much for watching. I hope you enjoyed this as much as I did. I'll probably do another one of these again, because this was a lot of fun to be able to laugh and explain these different things. But if you enjoyed this, check out some of my other videos. Here's a video that I made when I proved that 1 = 2. So this was last year's April Fools, so go ahead and watch it and see if you can figure out where the mistake is. And if that's not your cup of tea, go ahead and check out one of my other videos, and I hope you have a great rest of your day, and good luck with all of your math.